Welcome to the Deep Dive Generative AI Future Series. This is part 3. Today we're embarking on, well, a pretty transformative journey, I think. We're going to trace the path of AI models. From their early days where, raw size was king, often at an outrageous cost, to a cutting-edge future. A future where intelligence is not just massive, but remarkably efficient and remarkably smart in how it allocates its own processing power. Our mission for this deep dive to explore exactly what's at the forefront of AI model efficiency. We're going to unpack some truly revolutionary concepts, starting with the foundational idea of conditional computation, then moving into the groundbreaking mixture of experts, or MoE, and then finally peering into the very latest advancements with mixture of recursions, MoR. It's all about how we make AI smarter, right, without requiring unlimited computational resources or, frankly, an ever-expanding carbon footprint.
Exactly. It's precisely that core tension you just highlighted that defines this whole area of research. It really does. How do we build these, increasingly vast and capable AI models, models that can absorb immense amounts of information, learn intricate patterns, and achieve incredible feats like few-shot generalization and sophisticated reasoning, but without incurring absolutely prohibitive computational and memory costs? It's a huge challenge. For a long time, the prevailing wisdom was just scale up, right? Just make it bigger. But that scaling came at an almost unimaginable price, really. Today, we're going to pull back the curtain on some, well, truly ingenious solutions and some surprising facts, too. Things that are fundamentally changing that equation, making powerful, advanced AI not just a theoretical possibility, but a practical and deployable reality for a much wider range of applications than we could have imagined even a few years ago.
Okay, so for years, the mantra in deep learning was basically bigger is better, wasn't it? Just keep adding parameters, throw more data at it, and voila, performance climbs. It seemed almost like magic, but that, as you just hinted, definitely comes at a cost, often a very steep one. What was the fundamental challenge that really kicked off this whole efficiency revolution in the first place? What made researchers sit up and say, hold on, simply scaling up isn't sustainable?
You've hit on something crucial there. The critical dilemma is indeed this seemingly unbreakable link between capacity and computation.
Right.
While it's absolutely true that increasing model capacity, the sheer number of parameters has demonstrably led to vastly improved accuracy, especially when dealing with massive data sets, text, images, audio across the board. The traditional approach has a fundamental, almost naive flaw. In these conventional models, the entire network, every single parameter, millions, billions maybe, it's activated and processed for every single input example. Think about that.
Every single one. Wow.
Yes. Imagine, if you will, a massive, sprawling factory. Every single machine in that factory, from the smallest drill press to the largest assembly robot, is turned on and running at full tilt for every single product being manufactured, even if only a handful of those machines are actually needed for that specific item. It's
Sure.
madness,
Yeah,
well.
you'd have tremendous energy waste, unnecessary wear and tear.
Exactly. A lot of idle capacity just consuming resources. This always-on approach in neural networks leads to what the researchers at Google Brains so aptly described in their seminal 2017 paper, the one titled Outrageously Large Neural Networks, which is just a fantastic title. They called it a roughly quadratic blow-up in training costs. And this problem only gets worse as both model size and the sheer volume of training data continue to explode. It just compounds. It's a demand that even the most impressive advances in computing power, like more GPUs, distributed computation across hundreds of machines. Even those advances struggle to keep up. The sheer scale was quickly becoming unsustainable. We were hitting hard limits on both economic feasibility and, frankly, energy consumption.
That factory analogy really clarifies the inefficiency. It paints a very clear picture. So to combat this, the idea of conditional computation emerged as, well, a theoretical answer at first. It sounds incredibly intuitive. Only use what you need. Makes perfect sense. If a model is processing an image of a cat, it probably doesn't need to activate the parts specialized in, I don't know, human speech or financial analysis. How was this supposed to work in theory? What was the vision before it became a practical reality?
Well, in theory, conditional computation posits a neural network where large, distinct parts of it can be active or inactive on a per-example basis. The underlying idea was, as you said, intuitive, to dramatically increase model capacity without a proportional increase in computation. Think of it as that sprawling factory we discussed, but now redesigned. Smarter. Instead of every machine running, you have highly specialized workstations. And each workstation, or expert, as they started calling them, only spins up and gets to work when its specific skill set is required for the product currently being processed.
Right, like task specialization.
Exactly. This was the dream, essentially infinite capacity for finite computation, where you could theoretically add as many experts as you wanted, making your model capable of learning almost anything. But you'd only pay the computational cost for the specific experts needed for that particular input at that moment.
Okay, that makes sense.
Early theoretical proposals for this, they varied quite a bit in their implementation details. For instance, the gating decisions, how you choose which parts to activate, could be binary, a simple on or off. Or they could be sparse and continuous, meaning an expert might contribute, say, 30% or 70%, allowing for a more nuanced blend. And these activation decisions could also be stochastic, introducing some randomness to help exploration. Or fully deterministic, always picking the same experts for the same input. And the methods for training these gating decisions, the mechanism that decides what to activate, they ranged widely. Some people proposed using reinforcement learning, where the model kind of rewards itself for good choices. Others aimed for more conventional backpropagation, letting gradients flow through the gating mechanism itself. The promise was immense. Break free from that quadratic scaling barrier and unlock just unprecedented model sizes.
That theoretical promise really does sound like a silver bullet, almost too good to be true. But we know the path from theory to practice is rarely smooth, especially in AI. It's often messy. What were the significant practical roadblocks that kept these early conditional computing ideas from becoming widespread? Why didn't we see these infinitely capacious models popping up everywhere immediately after the idea surfaced?
That's a critical point. The gap between elegant theory and, as you say, messy reality, it was substantial. Several major challenges truly hindered those early attempts, and they weren't just minor kinks, they were fundamental architectural and engineering hurdles. Real roadblocks.
Like what specifically?
Okay, first, and perhaps this sounds a bit counterintuitive, modern computing devices, particularly GPUs, are much faster at arithmetic than at branching.
Master at math than deciding.
Pretty much. GPUs are designed for sheer parallel number crunching. Millions, billions of calculations at once, usually big matrix multiplications, that's what they're optimized for. But constantly checking conditions, is this part active? Turn this chunk on, off, for this specific input, and then dynamically reconfiguring the calculations based on those checks. That introduces significant overhead. It slows things down. It's like that super fast assembly line having to constantly pause, retool, and reroute based on individual item specs instead of just churning out standard parts.
Right.
That branching overhead could easily wipe out any theoretical computational savings you hope to get.
Okay, hurdle number one. The hardware wasn't quite built for it. What else?
Second, large batch sizes are critical for performance in deep learning. You need big batches. Training efficiently relies on processing many examples simultaneously. This amortizes costs, like moving parameters to the GPU and updating them. Big batches mean better GPU use, more stable updates, but conditional computation inherently fragments these batches. It shatters them almost. If only a small subset of the network is active, for an example, and you have, say, 1,000 experts, then each active expert only gets a tiny, inefficient sub-batch of examples. This is the shrinking batch problem. So while your overall model might be processing a large batch, each individual expert is basically sitting around waiting for enough work to compute efficiently. It slows down training dramatically.
Right, because each expert needs its own critical mass of data to be efficient.
Precisely. Third hurdle. Network bandwidth can be a bottleneck. Think about a cluster of powerful GPUs working together. Their raw compute power can be thousands of times greater than the speed they can talk to each other over the network. For conditional computation to work well, the amount of calculation an expert does internally has to be significantly larger than the amount of data it needs to send and receive. If an expert doesn't do enough thinking relative to its communication needs, it gets stuck waiting for data. It's bottlenecked by the network. Certain types of layers, like embedding layers which handle word meanings, often suffer from this. Their performance is limited by bandwidth, not compute.
Okay, so hardware branching, shrinking batches, network bottlenecks. Anything else?
Yes, one more major thing. Some early schemes required complex loss terms, extra mathematical objectives during training. These were needed to encourage the desired sparsity, using only a few experts per input, and, crucially, to ensure load balancing. You need to make sure the computational load is distributed evenly across all experts, not just having a few popular ones do all the work while others sit idle. Getting these extra loss terms right without messing up the model's overall quality or leading to skewed resource use was a really tricky balancing act. And remember, a lot of the early literature was focused on relatively small image recognition data sets. These just didn't stress test the systems enough or require the massive parameter counts where these problems become really acute.
Okay, so we had this brilliant theory, but these very stubborn practical problems. Branching overhead, shrinking batches, network limits, and the complexity of balancing the load. This sets the stage perfectly for the 2017 MoE paper by Google Brain.
Yeah.
You said they effectively cracked the code. How did they finally realize the promise that had been so elusive? What was the core innovation that finally made it work?
They introduced a new, highly effective, and actually quite general-purpose neural network component, the sparsely gated mixture of experts layer, MoE. The brilliance of it, I think, lies in its elegant yet powerful structure. It's clever. At its heart, a MoE layer has a number of experts. Each expert is typically a simple, independent feed-forward network, its own little brain with its own parameters. But the real magic, the secret sauce, comes from the trainable gating network. Its job is to intelligently select a sparse combination of these experts, maybe just one or two or maybe a few more, but never all of them, to process each incoming input.
So it routes the traffic.
Exactly. It's the traffic cop. For any given piece of data, a word, a sentence, an image patch, the gating network might decide, okay, send this one to expert number 7 and expert number 512 out of maybe thousands available. And what's absolutely crucial here is that all parts of the network, both the individual experts and the gating network itself, are trained jointly by back propagation. This joint training is key. It allows the whole system to learn together which experts are best suited for which types of data and how to route inputs effectively to maximize overall performance. The huge computational saving then comes simply from the fact that you don't evaluate the experts whose gate values are 0. If an expert isn't picked, its computations are just skipped entirely. Done. In their foundational work, they applied MoE convolutionally between stacked LSTM layers in big language models and translation systems, proving it worked in really demanding large-scale tasks.
That is incredibly clever. Skipping the unused part seems obvious now, but making it work is the trick. So this gating network, the traffic cop, how does it actually make its selections? Is it just a simple on-off switch? Or is there more nuance to how it writes the information?
Oh, it's definitely more nuanced than a simple switch. The evolution of that gating mechanism was a really pivotal part of their breakthrough. Initially, yeah, you could use a basic softmax gating. Takes the input, multiplies it by some learned weights, applies softmax, gets a probability distribution over all experts. Simple enough. But to get that crucial sparsity, making sure only a few experts are chosen, and also to proactively help with load balancing, they developed a more advanced technique called noisy top K gating.
Noisy top K. Okay, break that down.
Right. So it starts by adding a carefully tuned amount of Gaussian noise, just a bit of randomness to the scores for each expert before the softmax. This little bit of noise helps prevent the gating network from getting stuck always picking the exact same favorite experts. It encourages a bit more exploration. Then, after calculating these slightly noisy scores, it only keeps the top K values, say the top 2 highest scores if K2. And here's the clever bit. It effectively sets all the other scores to negative infinity, which, after the softmax function, makes their gate values exactly 0, guaranteed sparsity.
So the noise helps spread the load, and the top K enforces sparsity.
Precisely. The noise term helps with load balancing by subtly nudging the choices around, preventing a few experts from hogging all the work. And what was really fascinating was their practical observation. The discontinuities caused by this hard sparsity, this abrupt zeroing out, didn't actually cause major problems during training, which many might have expected. And crucially, gradients still flow back through this noisy gating network. It learns, it gets trained alongside the experts. This was a big advantage over some earlier methods that use trickier things like Boolean gates or reinforcement learning, which are often harder to train effectively.
Okay, so they had smart expert selection with this noisy top K gating.
Yeah.
But they still had to overcome those fundamental engineering hurdles you mentioned earlier, the shrinking batch problem and the network bandwidth constraints. Those didn't just disappear, right? How did they manage to solve those, turning this from a clever layer into a massively scalable reality?
Right, those hurdles were still very real. And this is where the engineering ingenuity and deep understanding of distributed systems really came into play. It wasn't just algorithmic cleverness. For the shrinking batch problem, remember, where each expert gets only a tiny fraction KBN of the total batch B, their solution was remarkably elegant. They basically said, okay, if each expert needs a bigger batch, let's make the overall batch size much, much larger and coordinate work across many machines. They achieved this by mixing data parallelism and model parallelism.
Mixing data and model parallelism. How does that work in this context?
So instead of having multiple model copies running totally independently, which is pure data parallelism, they set it up so that multiple data parallel model copies, each processing its own slice of the big data batch, would synchronously combine their relevant examples just before the MoE layer. Imagine you have D GPUs. Each processes a batch B. When they get to the MoE layer, they all effectively pool the examples that need to go to, say, expert 5. So expert 5 now receives examples from all D devices. This means each expert effectively gets a much larger, more efficient batch, roughly KBDN examples. The effective batch size per expert gets multiplied by the number of devices.
Wow, okay, so they use the distributed setup to solve the batch size problem for the individual experts.
Exactly. This clever coordination allowed them to scale up the number of experts, and thus parameters, proportionally to the number of devices, while keeping the memory footprint, the network bandwidth use, and the time per training step roughly constant on each device. It was a breakthrough for scaling. This technique was explicitly designed with the goal to train a trillion parameter model on a trillion word corpus, a scale that was just mind-boggling before MoE.
Okay, that handles the batch size. What about the network bandwidth bottleneck? Did that require a different trick?
Yes, they tackled that by designing the experts themselves to be computationally dense. Fat, you might say. They made sure each expert may be a feed-forward network with a large hidden layer. Thousands of units performed a substantial amount of internal calculation relative to its input-output size. This design ensured that the ratio of the expert's internal computation to the size of its input-output data was greater than the device's compute-to-network capacity ratio. In simpler terms, the experts did so much internal work that the time spent waiting for data to arrive over the network became much less significant compared to the time spent actually computing. It's like making sure each truck on your data highway is absolutely packed full before it leaves, making the trip worthwhile and overcoming that bandwidth limitation.
That makes sense. Make the work worthwhile for the communication cost. Now, with potentially thousands or even tens of thousands of experts, and this smart gating network choosing maybe just a couple, it seems like a real risk that a few star experts might end up doing all the heavy lifting, right? While others just sit idle, become dead experts that are never used. How do they ensure a balanced utilization across all these available experts? How do they prevent that kind of dominance?
That's an extremely critical point, and yes, it's something they observed happening naturally. The gating network does tend to favor certain experts. It becomes a self-reinforcing cycle. The favored experts get more training data, they get better, so they get picked even more often. To counteract this, they introduced an ingenious soft constraint approach, using 2 additional carefully designed loss terms added to the main training objective.
2 extra losses, okay.
First, there's a loss term they called l'importance. It works like this. They define an expert's importance for a batch as the sum of all the date values assigned to that expert within that batch. The importance loss then penalizes large variations in these importance values across all the experts. Mathematically, it minimizes the square of the coefficient of variation of these importance values. Essentially, it encourages all experts to have roughly equal total weighted input by penalizing big differences. It's like gently nudging the gate to spread the attention more evenly.
Okay, so equal importance. But does that guarantee equal workload?
Not necessarily. That's the subtle part. An expert could get high importance from just a few examples with very large gate weights, while another gets the same importance from many examples with small weights. This can still lead to an imbalanced computational load, the actual number of examples processed, and that's bad for memory and performance on distributed hardware. Some experts get overloaded, others are idle. So they introduced a second loss function, load. This one explicitly aims for balanced loads. It tries to ensure experts receive roughly equal numbers of examples. Since the actual number of examples is a discrete quantity, you can't backpropagate through counts directly, they use a clever, smooth estimator for the load. And the noise in the gating function actually helped make this estimator work well. This combination of importance and load was really elegant. It effectively forced the model to distribute the workload fairly, preventing expert dominance and ensuring efficient, balanced use of all that expensive distributed hardware.
So with all these pieces in place, the sparse gating, the clever fixes for batching and bandwidth, the balancing losses, it sounds like a really robust system.
Yeah.
What were the actual results? What tangible improvements did MoE deliver on those critical AI benchmarks like language modeling and machine translation? Did it live up to the hype in practice?
Oh, it absolutely did. The results weren't just incremental improvements, they were genuinely groundbreaking. They demonstrated significantly better results than state-of-the-art at lower computational cost. Across the board. Let's look at the 1 billion word language modeling benchmark first, a standard testbed. Their MoE models achieve dramatically lower perplexity. Remember, lower perplexity means the model is less surprised by text, so it understands and predicts language much better. The largest MoE model they tested, their 4Norny96 experts, 4.3 billion parameters, showed an impressive 24% lower perplexity compared to the strong baselines at the time. That's a massive jump in quality.
24% lower is huge in language modeling.
It really is. And even more striking, a high-budget MoE model achieved a perplexity of 28.0. The best previous result from a competitor was 30.6. But here's the kicker. The MoE model achieved this better result while requiring only 6% of the computation for 10 training epochs.
6%, that's incredible efficiency.
94% less compute for a better model. It was astounding. And when they scaled up to an even larger data set, the 100 billion word Google News corpus, a model with an incredible 65,536 experts translating to 68 billion parameters, dropped perplexity 39% lower than the computationally matched baseline. This has just hammered home the point. MoE let you use vastly increased capacity effectively, leading to huge quality gains on massive data sets.
Okay, impressive on language modeling. What about machine translation? That's another notoriously hard task.
Similar story there. On the widely used WMT14 English to French benchmark, an MoE model with 2048 experts hit a BLEU score of 40.56. BLEU measures translation quality against human references. This score represented a significant gain of 1.34 BLEU points over the previous state-of-the-art Google Neural Machine Translation GNMT models. That's a very noticeable improvement in translation fluency and accuracy. And this was achieved with 8.7 billion parameters just in the MoE layers, a scale that was previously very difficult to manage efficiently. The benefits even extended to multilingual machine translation. This is really cool. A single MoE model trained on multiple language pairs beat a specialized multilingual GNMT model on 11 out of 12 language pairs, sometimes by huge margins, like nearly 6 BLEU points. And incredibly, it even beat the monolingual GNMT model specifically trained for just one language pair on 8 out of 12 pairs. Plus, it achieved 19% lower perplexity overall. These results were just undeniable. MoE delivered unprecedented model capacity, leading to superior quality without that crippling computational explosion. It really was a game changer, opening the door to the truly massive models we see today.
Right, MoE clearly revolutionized things back in 2017. It made massive models practical. But then, as you mentioned, came the era of even bigger transformers. Hundreds of billions, even trillions of parameters, unlocking amazing things like few-shot learning, advanced reasoning. It feels like we solved one scaling problem, only to add another one, maybe at a different level. What new challenges emerged with these monster transformer models that MoE alone couldn't fully address? What led to the need for something like Mixture of Recursions or MoR? What was still missing?
That's an excellent way to frame it. It's like climbing one mountain peak only to see a taller one ahead. If we connect this to the bigger picture, while transformers indeed scale to truly incredible sizes, unlocking these impressive few-shot generalization and reasoning abilities that really redefined AI capabilities, they came with, as you implied, immense memory footprint and computational requirements. Just huge. Their sheer size and the quadratic complexity of the attention mechanism made training them and especially deploying them outside of, giant hyperscale data centers incredibly challenging, often prohibitively expensive. It's like having this unbelievable superbrain, but it's so resource hungry that only a handful of giant tech companies can afford to feed it.
So the access was still limited despite the capability.
Exactly. And the efficiency efforts in the transformer era tended to fall into one of two camps. Either people focused on parameter efficiency, things like layer tying, weight sharing, trying to reduce the number of unique weights the model has to learn and store, or they focused on adaptive computation spent in compute only when needed. Think of early exiting models that start processing a token once it's confident about the output, kind of like MoE, but often applied differently. The crucial missing piece was a truly unified architecture, something that could achieve both parameter efficiency and adaptive computation simultaneously within a single coherent framework.
Unifying those two goals.
Yes. Recursive transformers models that repeatedly apply the same shared layers offered a strong foundation for parameter efficiency because weight sharing is built in. But earlier attempts at dynamic recursion, where different tokens could loop through the shared layers a different number of times, those faced significant practical hurdles. They often required complex training setups or were difficult to deploy efficiently. It became clear that a more integrated, elegant approach was needed to combine these ideas effectively.
Okay, so MoR aims to bridge that gap, unifying parameter efficiency and adaptive computation.
bringing it all together. How does it actually manage that? How does it combine reusing parts and deciding how much work each part needs? It sounds like giving the model the ability to dynamically think harder when necessary.
That's precisely the core idea. MoR is a framework built cleverly on top of recursive transformers. So first, for parameter efficiency, it inherits the recursive structure. It reuses a shared stack of layers across recursion steps. Instead of dozens or hundreds of unique layers, you might have just a few blocks of layers that get applied repeatedly. This drastically cuts the number of unique parameters. Big memory savings, easier training.
Okay, that's the parameter efficiency part from recursion.
Right. But the real innovation, the MoR twist, is adding lightweight routers. These routers dynamically assign different recursion depths to individual tokens. Think about how you solve a complex problem. Some parts need deep, careful thought, maybe several passes. Other parts you glance at, understand immediately, and move on. MoR lets its tokens do something similar. Instead of every single token going through the exact same fixed number of processing steps, like in a standard transformer or even a basic recursive one, some tokens, maybe the more complex or important ones, get routed for more thinking steps. MoR passes through those shared layers, while simpler tokens can exit early, having received enough processing. That's the adaptive computation piece.
So it's adaptive per token in terms of processing depth.
Yeah, exactly, per token. And this dynamic routing is incredibly powerful for efficiency. It allows MoR to focus that computationally expensive quadratic attention computation only among tokens still active at a given recursion depth. Attention scales badly with sequence length. By pruning the set of tokens that need attention at deeper levels, you save a ton of computation. And it also dramatically improves memory access efficiency. It does this by selectively caching only their key value pairs, the attention memory, for just those tokens still active at that depth. This means less computation and significantly less memory needed for that infamous KV cache bottleneck. They even include a KV sharing variant specifically designed to cut pre-fill latency, the time it takes to process the initial prompt, which is critical for interactive apps. So in essence, MoR nails three things in one architecture. 1, ties weights to cut parameters. 2, routes tokens to cut redundant FLOPs. And 3, caches key values recursion-wise to cut memory traffic. It also conceptually links to this idea of latent space reasoning, letting the model perform adaptive, iterative thinking during decoding, making its process more efficient and maybe even more interpretable.
Okay, before we get deeper into the dynamic routing, let's just make sure we understand the recursive foundation. How do these models actually reuse or share layers to get that parameter saving? You mentioned shared blocks.
Yeah, exactly. Think of it like the model is partitioned into, say, NOR recursion blocks, instead of each block having totally unique layers. Each block utilizes parameters drawn from a shared pool. It's like having one really versatile toolkit that you use repeatedly for different stages of a build, rather than needing a whole new set of tools for each stage. This dramatically cuts the total parameter count compared to a standard transformer where every layer is distinct.
And are there different ways to share those parameters?
Yes, the paper explores 4 main strategies. There's cycle sharing. You might have layers 0, 1, 2, and then those same parameters are used again for layers 3, 4, 5, and so on in a cycle. Then there's sequence sharing. You reuse the same layer consecutively. Layer 0 gets used multiple times, and layer 1 gets used multiple times, etc. And then they have middle variants of both, middle cycle and middle sequence. These are a bit more nuanced. They keep unique parameters for the very first layer, often an embedding layer, and the very last layer, often the output projection. But they share weights cyclically or sequentially for all the layers in between. This gives you the benefit of specialized input-output processing while still getting massive savings in the middle. Empirically, they found that middle cycle sharing worked best, achieving the lowest validation loss. It seems that blend of unique ends and a cyclically shared middle was the sweet spot.
And this sharing helps more than just memory, right? You mentioned distributed training.
Absolutely. Techniques like FSDP, fully sharded data parallel, which distribute model parameters across GPUs, become much more efficient. Why? Because the parameters you gather onto a GPU for one recursion step are just reused for the subsequent steps within that same forward-backward pass. It multiplies the efficiency gains. And for inference, it enables something called continuous depth-wise batching. Because all recursion depths use the same shared parameters, you can actually batch together tokens that are at different stages of their recursive journey. This keeps the GPU constantly busy, filling in gaps left by tokens that finish early. It's a huge win for throughput.
Right, okay, the recursive foundation is clear now. Shared blocks, different sharing strategies, benefits for training and inference. Now for the really adaptive part. How does MoR decide how many thinking steps, how many recursions each individual token needs? It's fascinating that the model can dynamically adjust its own compute based on the input's complexity. How does that decision process work?
This is where MoR really gets interesting, giving the model that sort of metacognitive ability. It uses two main routing mechanisms to assign these token-specific recursion depths.
Two mechanisms.
Okay. First, there's expert choice routing. This is inspired by some other mixture of depths models out there. In this setup, each recursion depth itself acts like an expert. At each step, a lightweight router calculates a score for every token currently active. Based on these scores, the router at that depth selects its preferred top stat tokens to proceed to the next recursion step. So as you go deeper, the number of active tokens naturally narrows. The model focuses its resources on the tokens deemed most important or difficult at that stage. A key advantage here is that expert choice guarantees perfect load balancing. The router explicitly decides how many tokens go to the next depth, so you don't have depths getting overloaded or sitting idle.
Guaranteed load balancing sounds good. Is there a catch?
There is. The catch is potential causality violation during training. Because the router's decision about which tokens are top K at a given step might implicitly depend on information from tokens that appear later in the sequence, which wouldn't be available during real step-by-step inference. To deal with this, they had to use mitigation techniques, like adding an auxiliary loss function or a separate auxiliary router during training, basically teaching the main router to make decisions that respect the causal order of generation.
Okay, so expert choice. Good load balance, but needs careful handling of causality. What's the second mechanism?
The second one is token choice routing. This is simpler conceptually. Here, each token makes a single decision right at the beginning. How many recursion steps do I need? It gets assigned a fixed recursion depth from the start. So a token might decide I need 3 steps, and it goes through exactly 3 shared blocks and then stops. Another might say I only need 1. This completely avoids the causality issues of expert choice because the decision is made once, based only on the token's initial state. But the trade-off is that you typically need a balancing loss or other algorithms to manage potential load imbalance. There's no guarantee that the depths, the experts in this view, will receive an equal number of tokens naturally. You have to encourage balance. Their experiments showed that for expert choice, using that auxiliary loss worked best. For token choice, adding a balancing loss was effective for getting stable and accurate routing, even though balancing these different depth experts was initially tricky. It's a really interesting design choice with clear trade-offs.
Fascinating trade-offs. Okay, and one more critical piece. The KV cache, that memory monster. How does MoR tackle that notorious KV cache memory issue, especially when tokens have different dynamic depths? That seems like it could get complicated fast.
You're right to focus on that. The KV cache storing the key and value representations for attention is often the biggest memory hog, especially with long sequences. MoR tackles this directly with 2 tailored strategies.
2 strategies for the cache, too.
All right. The first is recursion-wise KV caching. This is quite intuitive. It selectively caches KV pairs, meaning the KV pairs for a token are only stored at the recursion depths that the token actually visits. If a token exits after step 2, its KV pairs are not stored for steps 3, 4, etc. They're just discarded for those deeper levels. This is hugely efficient. It significantly reduces KV memory and I/O, the storage and data movement, by roughly half or more, depending on the number of recursion steps. It also cuts down the attention FLOPs quadratically, because attention is only computed among the smaller set of active tokens at each depth. This makes handling much longer contexts feasible within reasonable memory limits, boosting both training and inference.
So you only cache what's needed where it's needed. Makes sense. What's the alternative?
The alternative is recursive KV sharing. This one is even more aggressive on memory saving. Here, you only compute and store the KV pairs from the very first recursion step. Remember, all tokens go through at least the first step. These initial KV pairs are then reused across all subsequent recursion steps for the tokens that continue deeper. This offers maximal memory savings, potentially huge, and can also speed up inference by skipping KV projection and prefill calculations after the first step. However, the reduction in attention FLOPs is less dramatic here, only linear with the number of active tokens. And you can still face high KB data transfer I/O bottlenecks for very long sequences, even if storage is low. And crucially, the paper notes an interesting interaction. KV sharing degrades expert choice but benefits token choice routing in MoR.
Well, that's interesting. Why?
It seems the more precise, depth-specific routing of expert choice benefits more from having tailored KV caches at each depth, whereas token choice, making its decision early, might leverage the broader context from the shared first-step KVs more effectively. Again, it highlights these nuanced design trade-offs depending on the exact MoR configuration.
Right, the details really matter. Okay, so the theory and mechanisms behind MoR sound incredibly sophisticated, integrating recursion, dynamic routing, clever caching, multiple layers of efficiency working together.
Huh.
But the proof is in the pudding, right? What did MoR actually deliver in experiments? Did it truly live up to that promise of achieving large model quality with less cost?
It absolutely delivered. The empirical results were really strong, showing MoR carves out a new, better position on that compute versus quality curve. Let's look at the numbers. When comparing models trained with equal training FLPs, a fixed computational budget of 16.5 exaflops, MoR models, even with significantly smaller model sizes, like an 118 million parameter MoR2 versus a 315 million parameter standard, Transformer achieved significantly lowered validation perplexity and improved few-shot accuracy. For instance, that smaller MoR2 model got 43.1% few-shot accuracy, while the much larger vanilla baseline got 42.3%. Better results with almost 50% fewer parameters.
Now, how does it manage that? Better results with fewer parameters.
The key is efficiency. MoR's higher efficiency meant it could process more training tokens within the same FLP's budget. It learned more from the same amount of computation. And even when they controlled for the number of training tokens seen, 20 billion tokens for both, the MoR models, with 2 recursion steps, still outperformed the baselines despite using 25% fewer training FLPs to process that same amount of data. And that translates directly to real-world savings, 19% reduced training time and a 25% cut in peak memory usage. For anyone training these models, that's huge. Faster experiments, lower cloud bills, or the ability to train bigger, better models on the hardware you already have. It really showed MoR provides a superior compute accuracy trade-off.
Those are massive savings, especially on the pre-training side, which is notoriously expensive. But what about using the models? Beyond training, does MoR make these powerful AI models faster in the real world during inference? That's critical for deployment.
Absolutely. This is another area where MoR shines thanks to that continuous depth-wise batching we touched on earlier. Remember, when tokens finish their required recursion steps and exit early, they leave empty slots in the processing batch. MoR cleverly fills these vacant slots immediately with new incoming queries or tokens that are ready for their next step. It keeps the GPU pipeline packed and busy. No wasted cycles. This dramatically boosts inference throughput. All the MoR variants they tested consistently outperform the vanilla baseline in terms of speed, and as you'd expect, deeper recursion, allowing more steps, generally leads to more tokens exiting early, which further reduces KV cache pressure and compounds the speedup. For example, a MoR4 model allowing up to 4 recursion steps achieved up to a 2.06x speedup compared to the vanilla transformer baseline.
Or than double the speed. That's significant. Is there any quality trade-off for that speed?
Sometimes there can be a slight performance degradation when you push for the absolute maximum speedup by allowing very deep recursion. But often, this is considered a highly favorable trade-off for deployment. Gaining 2x speed for maybe a tiny, almost imperceptible drop in raw quality, most applications would take that deal in a heartbeat, especially real-time ones like chatbots or coding assistants.
Yeah, that makes perfect sense for practical use. So, stepping back, what does MoR tell us about the optimal way to scale AI models in the future? Does it change the calculus about just throwing more data versus building bigger models? It sounds like it might challenge the standard scaling laws.
It really does seem to challenge some deeply ingrained assumptions. MoR demonstrates a distinct compute-optimal scaling behavior. If you plot performance against model size parameters versus performance against training data size, MoR shows a larger slope on the parameter side. What that means is MoR models benefit more significantly from increasing their parameter count, specifically making that shared recursive block more powerful than they do from simply being fed more and more training data. In simpler terms, MoR appears to be less data hungry than vanilla transformers, relatively speaking.
Less data hungry. Why would that be?
The thinking is that because you're reusing that shared parameter block repeatedly, the inherent capability and reasoning power of that shared block itself becomes absolutely paramount. A more powerful shared block can perform more sophisticated thinking across its recursive steps. This suggests that the optimal scaling strategy for MoR architectures might be to favor allocating your precious compute budget towards increasing model capacity by using larger models trained for shorter steps. So invest more in building a bigger, smarter shared engine, even if you train it for slightly fewer epochs or on slightly less data compared to a vanilla model. It's a fundamental shift in how you might think about resource allocation for optimal results.
That's a really provocative insight about scaling. Focus on the engine's power. And finally, it's just incredibly intriguing that the model itself decides how much to think per token. You mentioned it reflects semantic importance. What patterns does this adaptive computation actually reveal about how the model processes information? And maybe more importantly, can we leverage that dynamic thinking at test time after it's trained?
What's truly fascinating is that the allocation of recursion depth clearly, visibly, reflects token semantic importance. It's not random. When you visualize which tokens get routed deeper, you see a very clear pattern. Content-rich tokens, key nouns, verbs, complex concepts like people, drugs, or even indicators like high confidence, these consistently undergo more recursion steps, maybe 3, 4, or more. The model is dedicating more internal thinking cycles to unpack their meaning or integrate them properly. Conversely, functional words and the, of, punctuation, or simpler concepts often require fewer steps, maybe just 1 or 2. The model processes them more quickly. It really shows this intelligent, adaptive allocation of computation based on the perceived difficulty or semantic value of each token. The model is self-regulating its cognitive effort.
That's amazing. It's like watching it decide where to focus its attention.
Exactly. And crucially, this isn't just a neat observation during training. MoR enables test time scaling via deeper recursion. This is a huge practical advantage. It means even after the model is fully trained, when you're actually using it for inference, you can choose to simply increase the maximum allowed recursion depth. You can tell the model, okay, for this task, think a bit harder. Allowing the model to perform more of these iterative refinement steps generally leads to improved generation quality, like better likelihood scores for the generated text. This ability to dial up the reasoning depth on demand without retraining is incredibly powerful. It positions MoR as a framework that moves closer to true latent reasoning, where the AI isn't just predicting the next token based on surface patterns, but is capable of more deliberate, iterative refinement of its internal understanding.
We've just completed an incredible deep dive, really tracing this evolution of efficient neural networks, from those initial, almost overwhelming challenges of outrageously large models and their costs, through the groundbreaking solutions like Mixture of Experts that made scale feasible, and now arriving at the unified, adaptive power of Mixture of Recursions. It's been quite the journey, honestly, revealing so much ingenuity.
Indeed, and if we connect this to the bigger picture, these innovations, they aren't just about making models bigger or faster in some abstract way. That's not the whole story. They're fundamentally reshaping how we even approach AI development. Shifting the paradigm, really, from just brute force scaling to much more intelligent, adaptive computation. They allow us, as the research shows, to achieve large model quality without incurring large model cost. That's a massive shift. And what that means is that advanced AI, with all its amazing capabilities, becomes more accessible, not just for big tech, but for more researchers, more organizations, and becomes more practical, more sustainable for a much wider range of real-world applications, far beyond the hyperscale data center.
So what does this all mean for us, the users, and for the future trajectory of AI? As these models keep getting more capable, but also simultaneously more efficient, more adaptive, learning to think only as deeply as needed for each specific bit of information. The real question we're left with, I think, is this: how will these breakthroughs transform our actual interaction with AI? Could it enable AI to move from being just a powerful, sometimes clunky tool to becoming a truly ubiquitous, seamlessly integrated intelligence? One that's woven into every facet of our lives, constantly adapting its own thinking to meet our needs, maybe without us even consciously realizing it's happening. The implications for how we work, how we learn, how we create, they seem truly boundless. It really makes you think.